Is born or just arises because of the competition of different terms in the model and describing the system. Just a little bit of technicality. An example of this sort is that if you imagine to have spin 1/2 arranged on a lattice that try to minimize the energy by aligning along the Z component and apply a magnetic field which is along the X component, then if this were classical spin, then nothing special would happen at t equals 0. But if these are, because of this being quantum, quantum spins, I mean, the system is unable to satisfy both terms in the Hamiltonian in minimizing them, and as a result, in a similar ways as at finite temperature, there will be a zero temperature transition governed by the interplay of the exchange and the external field. Now, this primarily thanks to Landau. It is by now well known that actually ordering, like in a ferromagnet or in a crystal, ordering is somewhat related to a symmetry which is spontaneously broken in the system. So for example, you take a lattice or just a bunch of atoms. When you go to a crystal-like structure, then even though if the Hamiltonian governing the interaction is invariant under space translations, the state of the system reorganizes itself by having less symmetry. So now it becomes invariant under translation of discrete, under discrete translation. So another example is a paramagnet. You have random spins or angular momentum pointing in any direction. When you cool down to a ferromagnetic, then the ferromagnetic states just choose a particular direction, therefore breaking rotational symmetry. This breaking of certain symmetry here, translational in space or rotational, is said to be spontaneous because it's not forced by any external means. It's not, for instance, in the case of ferromagnet, I'm applying a magnetic field to align all the moments, but it's rather a internal reorganization of the system itself that decides to enter a state with broken symmetry. So somehow more order corresponds to less symmetry. And here it comes the story of time crystal. If you explore, I mean, in the most diverse field in science, from condensed matter to high energy to whatever field you're thinking, there are zillions of cases in which certain symmetries were spontaneously broken, giving rise to certain type of orderings. Here I gave a very simple example. If you take a superconductor is related to the breaking of gauge symmetry. If you take liquid crystals, then you have much more complex symmetries. In high energy, I have no idea, so I will not say anything, but okay. That's it. So the question that actually Wilczek started to think about in this work of essentially 10 years ago was related to the fact that among all these many examples, apparently time translational invariance was never found to be spontaneously broken. Okay, so you take a system interacting balls. If they are in a fluid, then you have interacting balls with an interaction which is invariant under space translation. If this is a fluid, then there is no breaking of the space translational invariance. If they organize in a crystal, the system is less symmetric because you can translate of certain lattice vectors. In the same way, Wilczek said, okay, is it possible to have time translational invariance? If this is the case, then in analogy with space crystals, you just name this phase of matter should be called a time crystal. Okay? So this is a picture which means nothing, but it was put in the cover of Nature when these time crystals were observed for the first time. So this is the starting of this story. This paper by Wilczek, and at the beginning was not even clear if, say, nature would allow for such a phase. So it was not clear if the time crystals, this phase with the time translational invariance broken was never observed, was there because essentially the laws that govern our life and our world do not allow such a thing. If yes, and it's a yes, otherwise I would not be here to tell you this story, how to characterize and to define a time crystal. This is something which sounds so trivial now, but in the first 3-4 years of the discussion, it was highly debated, and I will try to explain why. Once you know that, at least in principle, such a time crystal may exist, the question was where to look for it. And here, the story about quantum simulators enters in the discussion. So actually, by now, we know that there is a positive answer to all these 3 questions, and I will concentrate mostly on those issues. Actually, but research in this trying to understand the property of time crystal is progressing, and actually I will try to tell you that some aspects of this phase has relation with things that we already know, and I will, if I have time, I will mention about synchronization. And finally, once you have a time crystal, is there something that it's useful for? Okay, and again, here there are some ideas, mostly related to either error correction or metrology, but essentially I will try to concentrate on the introduction to this, to the first 3 points. So just after this paper in 2012, there have been kind of hot, intense discussion. Here there are some of the names that at the beginning contribute to this topic. Try to understand what is a time crystal? And of course, there is some sociological aspects which are interesting, because Wilczek wrote few things which were wrong. But if Wilczek writes something which is wrong, it's stimulating. If we write something which is wrong, it's wrong. Okay. So luckily enough, then it was Wilczek. So people got excited in explaining that what he thought originally of a time crystal was simply wrong, and found a nice solution. So I will try to cover, so this is a long outline, but I will spend most of my talk just giving you some introduction to time crystals. Especially I will talk about these Floquet time crystals, which were those that were experimentally observed. And if I have time, I will mention something about these other things that are more related to what we know about synchronization. So let me start to explain, I mean, in a very idiotic ways, why there was a problem. Okay, so in order to, so if you want to say that the crystal has, so just a crystal, a space crystal, has is a state with the spontaneous symmetry, which is broken. You say, okay, I have the interaction describing so the potential describing the interaction between atoms. This potential is invariant under translation. Then I just look at the state of the crystal and I look at the density. The density will be something which is modulated. So it will have a peak where the atoms are, nothing in between. So the state of the system, this modulation does not respect all the symmetries of the interactions. Okay, so the state has spontaneously broken the symmetry. Okay, so then you say, okay, wow, that's the good idea. A good idea. Then I say, what is a time crystal? I start with a time independent model. Then, following the same idea of the density, if I find that there is some observable which is oscillating with time, then I'm done. Okay, because I mean, this, like the density is not obeying the symmetry of the Hamiltonian, but clearly, if this is the definition, it's not a good definition and trivialized everything. Because if you take any quantum, if you take a two-level system, you can always take any observable that will oscillate in time. Rabi oscillation exists, and nobody thought to anything related to spontaneous symmetry breaking. It's just related to the operator structure of quantum mechanics. Okay, so this type of approach is useless. So actually there were few couple of I would say 2 or 3 years of discussion. Let me skip this. So I mean, probably I will not go in these details, but actually at some point it was clear how to define, and actually the definition of spontaneous breaking of time translation was just a slight generalization of what has been known in many other cases. Essentially, just imagine, so this formula translates in this way. Just imagine you have magnetization, and you just, instead of looking at magnetization, you study correlations. So in a spontaneous symmetry broken state, then correlation will decay to a constant value when you just take these 2 points to infinity. So in a time crystal, instead of decaying to a constant value, which is the square of magnetization, it will decay to some oscillating function of time. So if you don't care, just don't care. I will not use this definition in the rest of the talk. What is very important is that once people understood how to define in a neat way what is a time crystal, there was this paper by these 2 Japanese people that proved a very interesting theorem. They show that if you take a system, any system, I mean, there are some caveats, but we'll forget about this. But any system which is in equilibrium, thermal equilibrium, or in the ground state, cannot break spontaneously time translational invariance. So if a time crystal would exist, it cannot exist in equilibrium. And this is a very important point because despite the fact that we are using similar names, space crystals or time crystals, the origin, so this analogy is not there. As a crystal is something which is in thermodynamic equilibrium. So I just take equilibrium thermodynamics and I describe solid, liquid, gas, whatever. A time crystal cannot exist in equilibrium. But it's still an open question to understand how to make it outside equilibrium. Okay, so if I take a system and I just force it by any means, I mean, by any means, to be in a non-equilibrium state, then there is the hope to find such a weird phase. For historical reasons, the first example of non-equilibrium state where a time crystal could exist as the one that goes under the name of Bloquet time crystal. There is a very simple idea behind. That is, you take a system which is quantum system, and you just drive periodically the model. So, for instance, if you have a spin 1/2, then, for instance, you just apply a pulse magnetic field. Okay, just a sequence of pulses at given interval of time. Okay, this is a driven system. So it is a conservative, it's a quantum conservative system. So it does not dissipate any energy. So if the Hamiltonian, if the magnetic field would be constant, this is a conservative system, but it's not because I just do this pulse at given time intervals. So the definition was done in a much more proper way, but the idea is essentially this. Just take a model and you just drive it with a given period. If the system breaks spontaneously this symmetry, then there should be some physical observables that will oscillate at multiples of the period. There are some important caveats that I will try to explain with a simple example. So these are phenomena. This is a phenomenon that we essentially know, which is called period doubling. So if you take nonlinear system, then it might be that you drive it with so if you take an harmonic oscillator, you drive it with a frequency and the system oscillates with the same frequency. But if you drive a nonlinear system, then it may be that the system responds with half of the frequency of what that you are applying. This is period doubling. Okay. So what is spatial? Spatial is that this period doubling emerges as a cooperative or collective effect from the many-body interaction. So it's not there. If you take 2 spins, 3 spins, and you drive it, you will never observe. And I will make a specific symbol example of this. But somehow, when you make the system larger and larger, there will be some internal reorganization that will lead to this period doubling. So this is not something quite common in a generic small system. Okay, so and the idea is very similar to something that we know. So just imagine that in space. Okay, so of course I just said that you should not make this analogy, and now I just use this analogy. Okay. So if you take atoms in a periodic lattice, sometimes they order in a charge density wave. So you see, you have 2 atoms every twice with twice the periodicity. This is exactly the same thing, but this again is an equilibrium phenomena. In time, is not an equilibrium phenomenon. So let me give you a specific, starting from a very simple example on how this will work. And then I will explain you why this is not a generic situation. Okay? So just imagine that you have spins. Okay, so they're interacting. So for the moment, I put the interaction of disorder for what I'm going to say later, but for the moment, you have just spins or angular moments which are interacting with some, so if they are parallel or anti-parallel, they get some J positive or negative. So you just let the system have this type of interaction and let it evolve for a certain time. So after some time, just take the spin and you flip them. Okay, just imagine that you know how to do it. It does not really matter for the moment. Okay, and then you continue. Okay, you just evolve. So those interact, then you flip, interact and flip. Okay, so you see this is a time periodic Bloquet evolution. Okay, where is the period? Oh, yeah. So the period is just this free evolution plus flip. But then let's see what happens to the state. I'm considering the trivial example. Okay, so suppose that I have a certain configuration of up and down. Okay, just evolve, since this is are untouched, they remain up and down. Then you flip and becomes down and up. Okay, in order to get the same state as before, you have to go to the second, so to twice the period. Okay, so you see that in this artificial and very fine-tuned dynamics, I constructed a situation in which I drive the system with a given period, and the state reacts in a way to go back to itself with twice the period. So you may say, good. Okay, so what is special? I can do this trick with 2 spin, 3 spin, so there is nothing special about all this. The special thing is that such a game is fragile to any possible imperfection I can imagine. Okay, in the sense that if this is not a perfect flip, but it's just the epsilon slightly different, or if you put any epsilon complication to this dynamic, so the state is not exactly this, whatever, this period doubling vanishes. Okay, this is some, you see, for this description, I did not even need to go to a large system. This works also for a single spin. So you need the extra ingredient to you need the extra ingredients to make this this mechanism robust. And these extra ingredients are very, very rare to be found in nature. So first of all, you see that if you have a conservative, a system which is conservative, and you just pump with the driving field, you are pumping energy. And if you are pumping energy, the system will sooner or later approach to a kind of effectively infinite like temperature state. So essentially, you need to find dynamics which are highly non-ergodic. So you want something which is a complex many-body dynamics, which does not lead to a thermal state. Something which was proposed in those two papers that, so actually the first, they were theoretical proposals. For reasons that I will not have time to discuss, if you put disorder, so if this interaction between spin has some disorder, then you enter a state which prevents the system to heat up. Okay? And this is something which can be realized. And actually, when you have such conditions, then you can also enter in a regime in which it's not that you have to find specific parameters or initial state. Okay? But the effect is rather robust. Moreover, something else which is non-trivial, as any spontaneous symmetry breaking phenomena, this period doubling should manifest only when you go to the thermodynamic limit. So let me stress once more that for this type of time crystal, you need to have a dynamics which is protected from the external environment. So it should be unitary evolution, should be many body in nature, should not lead to thermalization. This is extremely difficult, especially the fact that you have unitary evolution. So in nature, so if you take any bunch of spins, will have interaction in a solid with phonons, with all kind of additional external environment, which will essentially kill all these things. And that's the reason why, for instance, this Floquet, this first version of time crystal was never found in nature. This is a numerical simulation. This is not nature. But actually, this was exactly. So let me spend 2 minutes, 1 minute on this. So you just do. So essentially, you want to see this up and down with twice the the periodicity in a, and so this is just a few spins, 8, 10, 12 interacting in one dimensions. Okay. So what is called Z here, it is the analogous of staggered magnetization. So if you just put a minus sign every cycle and you just sum, then for a perfect period doubling, this would be 1. So the only thing which I would like that you pay attention is that you see that any system for some time will show this period doubling. But sooner or later, so for instance, take the smallest, the blue one, it will go to 0. Okay, so any finite system will eventually obey the symmetry of the evolution is subjected to. But you see that if you go to a larger system, the time over which this anomalous behavior persists increases. And actually, if you see, it increases exponentially with the system size. So if you would take 20, then it would go. And if you take infinite, it would go forever. Okay, so these are a few spins. It's a simulation. It's a simple. I don't know. It's a simulation. But this is the experiment. So after, I think, 2 years, actually, these are where the preprints was published. There were 2 papers, one in the group of Monroe, one in the group of Lukin, that did exactly what has been simulated in the numerics. They use 2 different quantum simulators. One was trapped ions. So you take ions, you trapped on a one-dimensional thing, and essentially 2 levels of each ion is the 2-level system, up and down. Okay. Then, so let me describe only this trapped ion case. And then what you do is you just, the magnetic field, the ions will interact because they are ions, so they repel, and this will lead to some interaction between the 2 levels. Plus, you just shine light on given atoms, and then this will behave like a magnetic field. And so in these experiments, essentially, they did exactly what I just described in words. In the sense, this was a quantum simulation. They took this real system, so it's not a computer, it's a real system, but they just designed in such a way to realize the type of symbol dynamics that they draw. Now, the only thing to pay attention to is that if there is so this is a kind of Fourier transform of this, correspond to this Z or whatever. But so essentially, if there is a period doubling, you should see a peak. Okay, so just telling that there is half of the frequency. Now, if you take independent spins, then there is no peak, essentially. Okay, so the system behaves like it should be. The period doubling manifests only if the system behaves as a real many-body system. So this was, so essentially the same dynamics was confirmed also in the experiment in Lugin's group on Rydberg atoms. So given the time, so 50 minutes and stop. Okay, so I will go very fast. I will just comment on this. So as I showed that, so this example that I gave you was possible only in a system which was perfectly protected by its environment. But the question holds. I mean, is it possible that that the environment is always a disaster? So actually, there is a number of papers on this that shows that if you take quantum many-body open system, then it is possible to have again these time crystals. And so don't read this because this is not clear at this stage. But again, in the same way I use the word period doubling, which is something more familiar. Here, if you take a many-body open system, the essence of time crystal is that the fact that the system develops limit cycles. So it does not approach to a steady state, but approach to a limit cycle in the thermodynamic system. I'll skip all this just to mention only recently. So last year there was an experiment with Bose-Einstein condensate in a cavity with driven laser, and they somewhat showed that by observing the oscillation of the photons in the cavity, they could relate this oscillation to the oscillation of a time crystal. I'll skip all this and go to my conclusions. So I just gave you some generic, some intro to time crystalline phase, which again was possible thanks to this, to all this fantastic progress in quantum simulators. I had no time to talk about this dissipative time crystals, but there are very interesting connection to something which we know very well in classical system, that is related to synchronization. What is very exciting is that there are already several experiments, and this may lead to some further progress, especially in trying to understand if this time crystal can be used for any application. So this, I think I would like to share this because I should acknowledge people with whom I collaborate on this topic. Essentially, we work a lot in Trieste with Marcello Del Monte and various other people that moved away in several places, but we had a lot of nice collaboration, and I really would like to take time to thank them for this. And with this, I thank you for the attention. Thank you. Are there questions?
Sal, thank you for your nice talk. Just an idea that I got while you were speaking. Is it possible to envisage something like your time crystals in nuclear physics, using, for example, isospin symmetry?
I cannot answer due to my ignorance. I should say, not because
isospin is much more like the normal spin, but more approximate, let's say, symmetry. So I was just wondering if we could get something like that in nuclei.
I have to. I mean, I want to discuss and no more because I'm not able to answer.
Okay, thank you.
Possibly it's not dissolved.
So disorder is not really important in the sense that if you find other ways to have to non-ergodic dynamics with some other constraints, then it's fine. So disorder is an easy way to implement this, but it's not.
Yes, thanks. First of all, thanks for your presentation. Sorry for my questions because I'm not completely involved in this field. This is the first time that I hear about time crystals. So maybe my question is or exactly so. My point was when I studied something about the spontaneous symmetry breaking, I studied something related with the I don't know, you have a system with a many-body system, and you preserve some quantity. No? Then at a certain point, yes, you have this big system that interact with all those particles, and like a magic appear, let's say spontaneous, the system spontaneous, which are void state, okay. Which is the minimum of this of the energetic configuration of the system. Now, my point is, you are practically switching the concept of space with the concept of time. And so my question was, in this case, the system is not, how to say, preserving the energy at all. In fact, that you are you are imposing a pulsing of this system. And my question was at the end, do you need exactly a pulsed a time dependent with a certain period timing the pulse, or you can define another system with a continuous
yes. Okay, so let me specify something. So the thing that you describe applies in equilibrium, where you say I have a minimum of the potential, okay, but in principle you can describe symmetry, spontaneous symmetry breaking in generic terms. So you have a certain dynamics which respects certain set of symmetries, and the system for some reason violate those symmetries. Okay, and this does not correspond to any minimization.
Okay.
Okay. And this is what and actually the fact that I'm considering non-equilibrium requires this. I don't have any energy to minimize. The second thing is actually related to the second part that I did not present, because continuous time crystal have been found in open systems.
Yeah, in part.
Okay.
Was,
yes.
My...
So where you don't need to impose a periodicity from the outside, and then the system reacts with double the periodicity.
Okay.
There are no examples of conservative system in which the time crystal is continuous. But it's not that I can tell you that somebody proved that they are not possible to, that don't exist. So far, nobody has a good idea. So I have no I have no idea how to find them there.
Okay, thanks.
Thank you very much for your nice talk. I have the following question. If we consider the quantum field theory, what would be the ghost from Boston in this case? Because we are breaking a continuous symmetry. Do we have any hint about that?
Yeah, so there was actually so essentially, so this is somewhat written this finite frequency criticality. So from structure, so we study an effective Landau functional, and this is something where the soft mode appears at finite frequency. So typically the soft mode appears at zero frequency, but zero momentum or finite momentum. The soft mode in this effective theory will appear at finite frequency.
Thank you.
I have that. No, Darius.
So, like a kinetic driven symmetry breaking, so finite frequency in that case is finite momentum.
Yeah, it's finite. Yes. But essentially you cannot. I mean, to get this, you have to go to Kadish because it's not equilibrium, so it's not something you get.
Just concerning open systems, I had the intuition would say that if you have some, say, low frequency noise or some disorder, low changing in terms of disorder, it should in principle help to improve this kind of phenomenon. So the question is that I think open system is Markovian. Is there any idea of non-Markovian situations?
So if you so non-Markovian is a zoo of infinite type of. So if you assume that non-Markovian is just a memory, let's assume this is not like this, but if it's just a memory effect, so essentially as long as the memory is shorter, much shorter than the period doubling, then I mean there may be quantitative correction, but nothing.
Non-Markovian, non-ergodic.
Non-Markovian, no, sure. If it's ergodic, then
yeah, okay.
The end of the story. If the memory starts playing, starts having an interplay with the natural period of the time crystal, this is an open problem. No, nobody knows.
And then, if I'm allowed, I have another question. Just you showed that for the XX Z model, and the curiosity is that in which phase are you? To which phase are you looking to? And is there anything special to expect if you are close to the phase transition?
No, I did not understand. So, which phase of what?
You showed the speed model.
Sorry, you have to be always in the MDA phase, because once you are away from MDA, MDA means many body localized things. Because the system, you should make the system unable to absorb energy.
Questions? If not, we thank again for the.
Ma scusa, tu puoi condividere lo schermo e non avere male. No, perché? Perché non so. No, avevo sente. Ciao. Ma che...